In this lesson we talk about function notation. And function notation is notation such as f at x. That's used to represent the value of the dependent variable, or the output, for the given value of the independent variable, which is x, and x is the input. So, in other words, f at x, written like this, is the output of a function, or the y value, that we get when we input a certain value for x. And usually when we think about the output of a function or the dependent variable, we think about y. But now we're saying we can also call it f at x. This is not a multiplication. We're not saying f times x. We're saying f at x. And this is a notation that you'll get used to in time. So typically speaking, we say that the value of the dependent variable is y, and now we're saying the value of the dependent variable can be thought of as f at x if the function is called f and if the independent variable is in terms of x, which it usually is. So since the dependent variable can be called y or f at x, then we often see written y equals f at x. Okay? And so we might say, well, is it always f? Does a function always have to be called f? And the answer is no. Just like an independent variable doesn't always have to be x, a function doesn't always have to be called f. F is the most common letter associated to a function, but sometimes you'll see g associated to a function. You might see g at x or h at x. Those are common ones, etc. Or maybe the independent variable isn't x. Maybe the independent variable is w, and we're talking about the area of a rectangle in terms of the width, expressed as a function of width. So the area expressed as a function of width. Or maybe we're talking about the temperature in Fahrenheit as a function of the temperature in Celsius. What's good about function notation is it gives you both the independent and the dependent variable. The independent variable is inside the bracket, and the dependent variable is given by, is alluded to by what's outside the bracket. So take for instance here, a at w. What that tells us is that the independent variable is w, and that the dependent variable is a value for the area. In another case, which we'll do later on in this same lesson, the independent variable is the temperature in Celsius, and the dependent variable will be the temperature that we get in Fahrenheit. So we input a Celsius temperature and we get out the Fahrenheit temperature. Or we input the width of a rectangle and we get out the area. We did examples like this a day or two ago in class. So let's do our first example together here. I'm going to show you the graph of a function, and we're going to determine the values being sought. So here's the function. Looks like this. And the question asks us, what does g at 3 equal? Well, we know that y is equal to g at x. So what we do is we say when x is 3, what does y equal? What is the value of the function when x is 3? Well, when x is 3, the value of the function, the y value, is 2. So when x is 3, the y value is 2. So g at 3 equals 2. Similarly here, what does g at negative 1 equal? Well, we're saying when we input an x value of negative 1, what's the value of the function? Well, when I input a x value of negative 1, the value of the function, or the y value, is 0. So g at negative 1 is 0. Now the next question says, if g at x equals 1, what does x equal? What does x equal if g at x equals 1? Well, this is like saying if y equals 1. So if y equals 1, what does x equal? Well, there might be one answer, or more than one answer, or no answers. Let's take a look. Let's take a look at every point on this graph where g at x, or the y value in other words, equals 1. right there. That's the only point with a y value of 1. So when g at x equals 1, the x value is 0. So what does x equal if g at x equals 1? X equals 0. And finally the question is, what is the domain and range of g at x? Well, we see from our domain and range work that we're moving to the right from -1 and inclusive of -1. So we can say that the domain is a set of all x such that x is greater than or equal to -1 and x is an element of the reals. And since this is the domain of the function g, you'll sometimes see a little subscript g underneath the d, like that. And similarly, what's the range of g? Well, the range of g is all the numbers from 0 and up inclusive. This is not a horizontal line. This is a line. This is a curve that will become infinitely high the farther to the right we go. So the range is all values of y greater than or equal to 0. So we write that the range is a set of all y such that y is greater than or equal to 0 and y is an element of the reals. And since we're talking about the range of the function g, you'll sometimes see a little g written as a subscript there. Okay? Now, for this next one, instead of having the function, in other words, the set of ordered pairs, given to us in terms of a graph, we have it given to us in terms of a polynomial. So we're going to imagine that the functions, two functions are given to us. F at x equals x squared minus 3x, and g at x equals 1 minus 2x. And what they want us to do is show that f at 2 is greater than g at 2, and explain what that means about their graphs. And then it wants us to determine g at 3b, and it wants us to also determine f at c plus 2 minus g at c plus 2. Okay, so let's take a look at how we'll do that. First of all, we want to know, we're going to show that f at 2 is greater than g at 2. Now, the question tells us that f at x equals x squared minus 3x. Well, what that means is that that means this. F at block is equal to block squared minus 3 times block. Okay? And no matter what is in the block, in the bracket, that goes here and that goes here. It takes a little getting used to, but let's see what that means. So f at x is x squared minus 3x. That means f at 2 is 2 squared minus 3 times 2. Well, 2 squared is 4, 3 times 2 is 6, 4 minus 6 is negative 2. So f at 2 is equal to negative 2. And what that means is that for this particular function, when the x value is 2, the y value will be negative 2. So that means the point 2, negative 2 would appear on the graph of that function. Now, we saw on the last page that g at x is equal to 1 minus 2x. Well, if g at x is 1 minus 2x, then g at 2 is 1 minus 2 times 2. Notice how we plugged in a 2 for each x. And so 2 times 2 is 4, so 1 minus 4 is equal to negative 3. So that means that on the function g, the point 2, negative 3 is on the graph. And so what we've just shown, since f at 2 is negative 2 and g at 2 is negative 3, we've shown that f at 2 is greater than g at 2. What does that mean in terms of the graph? It means that if we were to graph the functions, that when x equaled 2, the graph of f would be above the graph of g, because the graph of f would be at 2, negative 2, and the graph of g would be at 2, negative 3. Okay? Next question says, if g at x is 1 minus 2x, what is g of 3b? Well, let's go back a second ago to what we said. G at x equaling 1 minus 2x means g at block is equal to 1 minus 2 times block. Well, in this case, the block is 3b. G at 3b gets plugged in here and gets plugged in here. So 1 minus 2 times 3b is the same as 1 minus 6b. And we can't simplify that at all, so we simply say g at 3b is 1 minus 6b. When the next one says what is f at c plus 2 minus g at c plus 2? Well, let's figure out each one independently. If f at x is x squared minus 3x, that means f at block is block squared minus 3 block. Well, in this case, the block is c plus 2. So f at c plus 2 is c plus 2 quantity squared minus 3 times c plus 2. Now all we do is distribute and collect. C plus 2 times c plus 2 minus 3c minus 6, like that. We expand this here, and we keep that like it was, and we collect like terms, and we get c squared plus c minus 2. So f at c plus 2 equals c squared plus c minus 2. Well, what's g at c plus 2? Well, g at x is 1 minus 2x, which means g at block is 1 minus 2 block, which means g at c plus 2 is 1 minus 2 times c plus 2. Well, we then distribute that negative 2 into the bracket, and we get 1 minus 2c minus 4, and when we collect up our like terms, we get negative 2c minus 3. So we now know what f at c plus 2 is, and we know what g at c plus 2 is. Now we want to know what is f at c plus 2 minus g at c plus 2. So we simply figure it out. F at c plus 2 minus g at c plus 2 is this polynomial minus this polynomial. We distribute that negative sign in here, and we collect up like terms, and we can say that f at c plus 2 minus g at c plus 2 is equal to c squared plus 3c plus 1. And we get to our last example. In our last example, we're given a little piece of scientific information. When you want to convert a temperature from Celsius to Fahrenheit, what you do is you multiply the Celsius temperature by 9 over 5, and then you add 32. Well, we want to create a function to achieve that for any Celsius value. In other words, come up with an equation and put it in function notation form. Then, we want to use that function to determine the Fahrenheit equivalent of 30 degrees Celsius. Well, using a little bit of grade 9 principles, we know that if we're going to multiply the Celsius temperature by 9/5 and then add 32, what we're really doing is multiplying the Celsius temperature by 9/5 and adding 32. So we're saying that y is 9/5 c plus 32. And we might say, well, what is y in this case? And you would say, well, y is the Fahrenheit temperature. So using function notation, we can literally call it that. The Fahrenheit temperature in terms of the Celsius temperature is 9/5 c plus 32. Pretty cool, eh? So now what we can do is plug in a 30 for the Celsius temperature and see what the Fahrenheit temperature equals. What is the Fahrenheit temperature at a Celsius temperature of 30? Well, it's 9/5 times 30 plus 32. Because remember, if f at c is 9/5 c plus 32, then f at block is 9/5 block plus 32. And if we're going to find out what the Fahrenheit temperature is with a Celsius temperature of 30, essentially that means we're inputting 30. So 30 becomes the block. 30 becomes the block. And now we simply evaluate. 9/5 times 30 is 270 over 5 plus 32. 270 over 5 is 54, so 54 plus 32 is 86. So when it's 30 degrees Celsius outside, it's 86 degrees Fahrenheit, because f at 30 is 86.